Hello and welcome to our final project for ECE 5780. I'm Michael Kaiser.
I'm Jacob Bills.
All right, next slide, please.
So our idea was to do an official NASA rover where we could control it remotely anywhere via a server, that we could return I think like sensor data from the rover. So it will avoid collisions because there is a delay between the sending and we don't have like a live video feed or avoidance, and that it'll automatically return to a route after a collision. And so on the right, we just have kind of like the block diagram of our system where we have the STM32 working as the main brain, and then it integrates with the internet through UART through the Huzzah that connects to the server, and then our encoders are interrupt based and a PWM motor controller and a UART sonar and temperature.
So we had four main milestones for this project. The first milestone was to communicate via Wi-Fi with the STM. This was done using an Adafruit Huzzah board, and this implemented UART, so that was one of the labs. And then the second milestone was to process distance and temperature data. Our sonar chip came with an additional sensor that would have a temperature sensor, so we could read the distance from the sonar and the temperature from the same device. And this would be done every 250 milliseconds using an interrupt. So this milestone used timers, interrupts, and UART because the sonar was UART based. And our third milestone was to get encoder interrupts and integrate the system with Wi-Fi communication. So we had encoders on our motors to control distance and drive to a specific location, and then we would send the location over Wi-Fi. We also implemented a basic P-tuner to drive straight, and this system used interrupts as well. And then our fourth milestone was complete system integration. We implemented collision detection. So if an object was in the way when driving to the target, the rover would drive around it, and then location and temperature data was sent from the rover back to the server and laptop. And then lastly, we wanted to organize everything to be readable. And then, of course, all of our milestones made use of GPIO pins. Next slide.
Okay, so the final design is what it came out to. On the left, we have just a picture of our rover. On the right is the wiring diagram that shows we have the STM connected to a number of different systems, like the left encoder, the right encoder. Just for simplicity, just assume all grounds are connected by a common rail, and we only included like GPIOs or pins that we used on each of the boards. Like the Huzzah had a number of other pins, but we only made use of the TX, RX, and ground. And so the big thing was just making sure that we had all of the GPIO pins set up correctly, and that they had the correct like pull up, pull down configurations. And so for the difficult implementations, the first part that we had difficulty with was getting the actual networking set up and making sure that everything worked. We were able to communicate from our Python server to the Huzzah running C. And then after we had that basic communication, we had to get a protocol where we could accurately and reliably get the data back and forth in between and not have a lot of corruption or issues reading back and forth. And so we had to have the Arduino correctly parse whether we were trying to send it a command or we were trying to have it forward the command through to the STM. So some of the higher level like networking stuff just stayed on the Arduino and didn't need to be forwarded on. And then to get the server working from remote locations, we had to set up a DNS for the bills.inc as well as a network address translation to be able to access it from outside our local area network, and then port forwarding for security purposes to make sure that it wasn't exposed on the standard SSH port.
And then some additional things that were difficult to implement on the STM was there were multiple interrupt handlers, and these interrupt handlers often used many different variables that were shared between them. For example, the variables keeping track of encoder counts were used by multiple different functions and interrupt handlers. So keeping all of this organized became difficult. And then memory related bugs, of course, when using pointers, there's always the concern that you accidentally overwrite an address you did not mean to write to. And we did deal with this bug at one point. One of the most difficult bugs was getting the sonar to function properly when distances took a long time to read because it was either out of range or you're trying to read too quickly. It wouldn't give the sonar time to function and kind of jam the whole system. So implementing delays to allow the hardware to function properly was a difficult implementation. And lastly, we had to implement a P tuner to make the rover drive straight. We had two motors, one on each side, and without the P tuner, the rover would not drive straight. And overall, working with low quality mechanical parts, namely the motors were very low quality, made it difficult to drive straight and get it to behave as we anticipated. And also the low batteries voltage we were working with made it so we did not have long to work with the rover at full power. Next slide.
All right, so for our core conclusions, is we reached all the milestones we had like alluded to in the earlier slides. We were able to get communication working. We were able to connect to the drive motors and cause it to drive and control speed. We were able to do some simple maneuvers remotely, as well as avoiding automatic collisions. And then we returned the necessary sensor data in a timely fashion. And then all this took place like over the internet, and we didn't need to be in the physical presence of the rover.
Then future improvements, we would like to develop a GUI that we would be able to interact with the server code so we could send data to the rover via a GUI and then receive the location data and plot it on the GUI. We actually made a GUI and had it all ready to use, but we were having some difficulty getting it to work with the server data, and due to time constraints, we're not able to pursue that. Would also like to use better motors with an integrated encoders, so it'll be more accurate and just higher quality. More precision would make it easier to control the motors, and would also like to have large or increase the V motor for the drive system. We only use 4 AA batteries, which drains pretty quickly. If we had greater voltage, it would give us more time to work at full power, which actually helped a lot. It drove straighter, the tuner worked better, and overall it just functioned better when we had full power. Thanks for watching our presentation.